Last time we talked about a number of different sort of concentration type units. We talked about percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. Remember on this one, out of those kind of percent concentrations, really the bottom one here is really important. And you want to make sure that you do get both components of a solution. So you want to make sure that you do have the solute plus the solvent here. And the reason you do want to be careful with this percent concentration is typically speaking, in those type of problems, they will give it to you separate from each other. So because you kind of get the information separate, it's very common that people will sometimes just go by the solvent and not actually add those guys together. We also had percent volume to volume, which is the volume of the solute divided by the volume of the solution times 100%. So like the first one here is kind of like grams over grams. This one is typically milliliters over milliliters. And unlike the first one, I would say in most cases, you probably will be given the volume of the solution. You don't have to necessarily worry a lot about maybe they give it to you separate. Not saying they couldn't, but I would say in most cases, they probably will give you just the volume of the solution. So you have to be as careful as you do with the percent mass to mass. We also had percent mass to volume, which is our mass of the solute divided by the volume of solution times 100%. It's kind of like density. It's like grams over milliliters, essentially. And this one as well, since you do have the volume of the solution on the bottom, you usually don't have to worry too much about making sure you actually have the solution, not the solvent. Remember that if you had any of these guys, you can basically turn them into a usable sort of conversion factor by assuming 100. So if you had a 5% by mass sodium chloride solution, that basically would mean you have 5 grams of sodium chloride in 100 grams of solution. And again, you can use that like a conversion factor if you needed to. You could flip it around the other way as well. And you have the 5 grams of sodium chloride there on the bottom. You could do that really for any of those percentages. If it was 5% volume to volume, it would just mean that you have 5 milliliters of sodium chloride in 100 milliliters of solution. And if it was 5% mass to volume, it would mean that you have something like 5 grams of sodium chloride in 100 milliliters of solution. So as we talked about last time, sometimes it's easier to take a more dimensional analysis approach on some of these calculations and just use it as a conversion factor if possible. Again, because if you just kind of do opposites cancel in that dimensional analysis calculation, you might not have to worry about rearranging the formula correctly and stuff like that, or the equation correctly. You just know basically multiply on top, divide by the bottom, and that will kind of take care of the math part of it for you if you need to. After that, we really got into the big concentration unit of the season here, which is molarity, big M. And molarity is basically moles of solute over liters of solution. Most people will obviously just go with moles per liter. We do solve for really any of these three things. So if you wanted liters, which is a very common sort of calculation, you would take the moles divided by the molarity. If you wanted moles, which is a really common calculation, liters times molarity. You do need to make sure, as we talked about last time, that the volume is in liters, especially if you're using molarity sort of by itself, if you will, in this type of calculation. That is so all the units properly cancel out. So with molarity here, there's 2 common conversions that you don't necessarily have to do all the time, but are very commonly done. A lot of times you're given things in grams and has to go to moles. And again, that's going to be our molar mass from the periodic table that allows us to do that, and grams per mole as a conversion factor. So that's a very common sort of conversion that you need to do when you're doing molarity type problems. The other one as well has to do with the volume. I would say, as you probably maybe know from lab, you usually will collect the volume or sort of measure the volume in milliliters is a very common unit of volume. So going from milliliters to liters is a really common conversion that we use a lot in molarity. Again, it does need to be in liters if you're using molarity by itself so that everything cancels out correctly. Remember that if you did have a number like 4.5 molar sodium chloride, as I mentioned before, definitely would get rid of the big M when you're going to use it in a calculation and use both units in your calculation so you could clearly see where those units are. The number should always stay with the moles part, and it should always be 1 liter, basically, if you have the molarity given to you. As I mentioned before, it is extremely common that people leave the big M and all they think about is moles. They have no idea about the volume, where it's at, how they should cancel it out, how they should use it. So again, very commonly with that big M, people just think about moles and not really both units. This way, at least if you write both units, you have a pretty good shot there of seeing the liters and thinking about the volume part of it. You can also, if you're given the molarity, also take a dimensional analysis approach to your calculation. You could use the molarity like any other conversion factor. You could flip it on its head there, put liters up on top and the moles on the bottom. And once again, if you just take it like a dimensional analysis problem and canceling out units you don't want, keeping the units you do want, and setting them up opposites cancel, again, it will kind of do the rearranging part of the formula for you if you take that more of an approach when you do the problem. So again, without having to remember, should I be multiplying or dividing? If you just kind of set it up that way, that opposites cancel, again, it'll kind of almost take care of the math for you as you do the problem. Any questions on any of that stuff there that we talked about? Okay. So next thing we're going to talk about then is, I think where we left off, we also talked about as well, just a reminder, we talked about the molarity of ions as well. And remember, that is really based on kind of like stoichiometry, how the ionic compound breaks apart in solution. That is, again, where we find ions, by the way, is in solution floating around. So we have something like the sodium sulfate, that does break apart into 2 sodium ions and a sulfate ion. And again, the quick way, if you were interested in just the concentration or molarity of the ions present, and you knew the molarity of the whole guy, which we'll just say is 1 molar here, you could just do it, like I said, sort of like a mole to mole relationship. For every 1 mole of the whole thing, we do get 2 moles of sodium in this case. So if we were interested in just the sodium's concentration, we would have to multiply the molarity of the whole thing by 2, and that would give us that it is 2 molar for sodium ions. When we look at sulfate, it is a 1-to-1 relationship between those. So we basically take 1 times the molarity of the whole thing would give us 1 molar of sulfate. So when this goes for a swim, you get twice as much sodium ions floating around as you do sulfate ions. So the way concentration works, it kind of works that way. It is twice as concentrated in terms of the sodium ions that's in that solution as it is of the sulfate. And again, the idea there is when you take just one of those units and it goes for a swim, you are going to basically liberate 2 sodium ions per 1 sulfate ion that's floating around that solution. So kind of a twice that concentration of sodium as it is sulfate. Any questions on that there? Okay. All right, so now the next thing we're going to talk about is dilution. So very often times we do get solutions that are really concentrated. So they have a high molarity, for example. And a lot of times when we want to use solutions in the lab, we want to use a more dilute solution. So we go through a process known as dilution. And it's sort of like that example I mentioned maybe the other day. When you get the soda with all the ice, you leave it in your car and all the ice melts, right? And now your soda is a lot less strong than it was before. It's definitely more dilute from all the water that came from the ice. So in a dilution, we add more only add more solvent. So when we want to dilute something, we oftentimes will add more solvent. Again, not 100% of the time, but a lot of times that solvent is water. So when we go through a dilution process, we're just going to basically add more water, for example, to it. And what that will end up doing is lowering the concentration. The moles of solute that's there before is still going to be the same as it was after you do dilution. So if you had a solution like this, and if these circles were the solute, the smaller part of the solution that's basically dissolved in it, and you went through a dilution and added more solvent, you would still have those four little guys kind of floating around, dissolved in that solution. The only deal is you just added more water. Now, that will mean that the moles of solute before and after dilution will stay the same. The solute, by the way, in a solution is really the thing that's reacting. So when you have a reaction happens, when you put two solutions together, it's the solute molecules, the little guys that are dissolved in the solution that float around, that really does the reacting. Why does the molarity go down? Well, if we just look at the molarity equation with all of its words, moles of solute divided by liters of solution. Now, remember, again, our solution is made up of two things. This is made up of the solute plus the solvent, which means when we go through a dilution, the only thing that changes in the molarity equation is we add more solvent, and more solvents on the bottom. The bottom number gets larger. The molarity ends up getting smaller because the bottom number here gets larger. So we're dividing by a larger number on the bottom, brings the molarity number down. So that is why our dilution results in a lower molarity than we started with. Now, we could actually calculate that, and here's one way that you could do a dilution in a fancy thing here. This is a volumetric flask. Volumetric usually means expensive, and it usually has one line. And for example, that would be the line that represents the volume here, 500 milliliters. Usually go about 2 decimal places on volumetric. So what you would do is you take a little bit of the solution a little bit of water, add a little bit of the more concentrated solution, and then pretty much top it off with some more water. Give it a mix, shaky, shaky, and your molarity will come down. There is an equation that we could use to calculate how we could do a dilution or what's happening in dilution. This is what is sometimes referred to as the dilution equation. M1 V1 equals M2 V2. This is kind of before and then after the dilution. So this is basically our molarity and our volume before. This is our molarity and our volume after. Typically speaking, usually people for the ones will use the more concentrated solution, and this is usually your more dilute solution. Now, I will say a lot of people use this equation M1 V1 equals M2 V2 because out of all the units of concentration for solutions, molarity is probably your most common. So that is commonly the one used. There is a more generic dilution equation that you might see, which is C1 V1 equals C2 V2. It's basically the same thing, except C is here is just concentration, not necessarily molarity, and V is still volume there. That's because technically speaking, you could use any concentration unit you want in this equation. You could do percent mass to mass on both sides. You could do percent volume to volume on both sides, percent mass to volume. You could use molarity on both sides. It just needs to be obviously the same unit of concentration on both sides of this formula for it to cancel out correctly. Again, I personally roll with this one most of the time because in real life situations, most of the time you're probably using molarity as your unit concentration. And that's usually, kind of the one that you use. But if you like C1V1 equals C2V2, it's the same thing. Just for the C, use molarity if it's molarity. But again, you can use any other sort of unit you want. Now, earlier we talked about, in terms of molarity and volume, that if you are not doing a dilution sort of calculation and you're just using volume and molarity, it does need to be in liters so that these properly cancel out when you're doing it. Now, the one place where if you are doing a dilution and you are using this equation here, if you want, you could actually leave the volume in milliliters on both sides, or you could do liters. It's your choice, whichever way you want to do it. It will work out the same. The reason it works in this equation and why you should only do it in this equation and not if you're just doing molarity and not a dilution problem is, as I might have mentioned before, if you take milliliters and times it by molarity, you get millimoles and not just moles, for example, like you get over here. And it works okay in this equation because let's just say, for example, we wanted to solve for V2. So M1, V1, and we would divide M2 to this side. M2 would equal V2. Now, if you just put in the units here, molarity, and I did milliliters for my volume, and I divided by molarity, the molarities will cancel, and you'll just end up with milliliters as your units, which is perfectly fine. Now, if we were going to solve for, say, M2, that would be M1 V1 divided by V2 is equal to M2. And once again, if we just put the units in, molarity times milliliters, now we're going to be dividing by milliliters, and that is what makes it work if you want to leave it in milliliters. So because there's basically molarity and volume on both sides of this equation, you could actually leave it in milliliters. It just means the volume you get will be milliliters. But if you want to still convert it to liters, you could do that as well. The volume that you would get would be liters as well. So again, this would be the one place where you can use milliliters and molarity. But again, if you still want to use the liters, it's all good. If you are using only molarity and not doing a dilution equation or formula or problem, you 100% of the time should probably convert it to liters because that's going to give you the units that you most likely are looking for, which are moles. Any questions on that there? All right, so let's take a look at an example here. What volume of 19 molar sodium hydroxide must be used to prepare 1 liter of a 0.15 molar sodium hydroxide solution? Okay, so let's take a look. So in this case, we want to know what volume of 19 molar sodium hydroxide needs to be used to prepare 1 liter of 0.15 molar sodium hydroxide. So in this case, it's sodium hydroxide. It's sodium hydroxide. So we're not doing any type of reaction. Here we're just doing dilution. Our molarity or concentration gets smaller as we go there. So basically what we got going on here is we have a bottle sitting there of 19 molar sodium hydroxide. We want to make a new sort of container that has a volume of 1 liter or 1,000 milliliters and has a molarity of 0.15 molar. So this is going to be our dilution equation. M1V1 is equal to M2V2. Does it really matter which ones you call the ones and the twos? It really doesn't. Again, as long as you keep the numbers that go together. In most cases, the more concentrated one is going to be our ones. So M1 in this case would be 19. V1, we actually don't know. M2, which is the more dilute solution, 0.15, and V2 is 1 liter. So in this case, we are going to solve for V1. And when we do, we're going to divide this to the other side. And that will give us V1 is equal to M2 V2 divided by M1. Putting in our numbers here, M2 up on top, 0.15 molar. 1 liter divided by 19 molar. Here, the molarities are going to cancel, and the unit I'm going to actually be in this case, is going to be liters. And that will get me 0.15 times 1 divided by 19. It's going to get me 0.0079 liters. Or that is roughly 7.9 milliliters. If you times it by 1,000 to convert it into milliliters, as there's 1 liter. 1 liter equals 1,000 milliliters, basically. First off, any question on that calculation there? So what is that 7.9 represent? That 7.9 milliliters is of the sodium hydroxide. That is how much we're going to take out of the more concentrated guy and put it into our new solution. We're going to take out 7.9 milliliters of it. And this is going to allow us to basically make our more dilute solution. We're going to add water in this case. So we basically, should we add about 1,000 milliliters of water to this? The answer is no, you should not add 1,000 milliliters of water to this, because if I add 1,000 milliliters of water, I would have 1,000 milliliters of water and 7.9 milliliters, which is like 1,007.9 milliliters. And that is definitely more than what I want for my total volume. So to figure out how much water you need to add in this case, you would take your final volume you're looking for, which is typically your V2, minus typically your V1 value, 7.9. I'll do it in milliliters since a little less zeros to deal with. We'll do 1,000 minus 7.9. That means roughly I should put in there about 992.1 milliliters of water. So if I do that, go 992.1 milliliters of water with this, give it a good mixing at that point, I will then have a solution that has a total volume of 1 liter or 1,000 milliliters, and will have a concentration of 0.15 molar. Question on that there. So that is also a very common mistake that sometimes people make, which is, they go, oh, it's 1,000 milliliters. I just need to add 1,000 milliliters of water. But remember, that's your total volume that you're looking for. So you need to subtract it off. So this part here is very common to find the volume of water. In most cases, V2 minus V1. And I would say that as long as obviously V1 is your more concentrated and V2 is your more dilute, then it's that way, would be the right way there. Or you could do that basically more dilute minus concentrated. I will also say that a lot of dilution questions will ask that question. Is not necessarily a lot of times they'll ask, what is like V1 or something like that, but they'll ask, how would you make the solution, or they'll ask how much water you need to add to make that solution. So that's a very common sort of dilution question. Bless you. Any questions on that there? All right, let's take a look at another one, which maybe that happens. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution if you had a 5 molar calcium nitrate solution? All right, let's take a look. So again here, calcium nitrate, different concentrations. So dilution happening here. Again, I'm going to go with the more concentrated guy as my M1. Here we do not have V1. We do have M2, which is the more dilute. And we want to make a 500 milliliter solution of it. So kind of the same setup here. We got basically a more concentrated 5 molar calcium nitrate solution. We want to make, again, a new one that has a molarity of 0.25 molar and a volume of 500 milliliters. So here we're going to solve for V1 again. And again, solving for V1, we're going to divide this to the other side. That's going to give us M2, V2, M1. Putting in our numbers here, we will end up with a V1 that is equal to 0.25 molar. Once again here, it is okay in this formula to leave the volume in milliliters. It just means that when I get my answer, they will be in milliliters. If you want to convert it to liters, that's also perfectly fine in this formula. It just means when you get your answer, you will be in liters. So it's just your preference there. That again is because I'm going to be dividing here by the molarity. And what that's going to do is essentially cancel those guys out. And that will leave me milliliters as my answer. Again, here, if you convert it to liters, your answer would be in liters at this point. And that's going to get me here 25 milliliters of calcium nitrate. Now, again, what that means is you would be going to your more concentrated bottle and you would be putting in there 25 milliliters of it. That is not the answer to the question it's asking, right? The question here is actually asking for the volume of water that we need to put in there. So we want to make sure we answer that question. So here, the volume of water in this case would equal V2 minus V1. And that means that I have already put in there, I'm looking for V2, which is 500 milliliters. I've already put in there 25 milliliters. That means I need to pop in there about 475 milliliters of water to go with that. So 475 milliliters of water. That's going to give me a total volume here of 500. And once again, once I mix that together, I will now have a solution that has a molarity of 0.25 molar. Question on that there, or dilution in general. So again, that's a very common question in dilution problems, how much water or solvent that you add. So you got to make sure you do read the questions carefully on these, because sometimes people will just circle 25 and call it a day after they put it into the formula. Any questions on that there? All right, the next thing we're going to talk about is some properties of solutions. One sort of property is a semipermeable membrane. And a semipermeable membrane is basically a barrier that has, and again, might not be super visual to your naked eye, but it's sort of a barrier that has kind of holes in it. And it has holes in it that allows certain size molecules to sail right through to the other side. It also would obviously exclude a little larger molecules from making it through those holes. And, like in your cells, they have membranes, allow certain things to flow in and out. And that's sort of the same idea here. Now, when we look at solutions, sometimes solutions are classified as are similar to solutions. They are what are referred to as colloids. And colloids are much larger than solute particles in a solution. They are large molecules like proteins, groups of molecules, or ions. They are homogeneous, which means they do look the same throughout. And they do not separate or settle out, but they are small enough colloids to pass through like a membrane. Pass through a membrane. Sorry, let me say that right. They're small enough to pass through filters, like a filter paper, but they're too large to pass through a membrane. So colloids will be able to pass through filters like filter paper if you use a funnel to funnel it and filter it. But they're too big to pass through those semipermeable membranes. Now, suspensions, on the other hand, are heterogeneous sort of mixtures. And when you look at it, it does not look the same throughout. And they are very different than solutions and colloids. They're also usually very large that you can see it with your naked eye. Hypothetically speaking, if you took some sand and water, sand would be a suspension. You could see the sand floating around, not really floating around, but you can see the sand in the water. And they are too large to be filtered out. So if you try to filter out sand, it's going to get stuck on the filter paper, so it won't go through. And obviously, they would also be too large to go through membranes. So solute molecules, which are small enough, and solvent ones usually can kind of go through your membrane. Colloids could go through filters, but not membranes. And suspensions pretty much get stuck everywhere because they're really large and stuff like that. Hypothetically speaking, maybe this week you're doing that lab and I think you add sand, so that would be your suspension, as it won't go through anything basically. So here's sort of the difference there. We have our suspension that will settle out. Also, when you get kind of liquid medication, right, you got to mix it up, right? There's suspension in there. You have solution and colloids that will float around. If you put it through a funnel with filter paper on there, you can see that both the solution and the colloids will go through. But here again, our suspensions are going to get caught. And this is also a like dialysis sort of bag, which is a semipermeable membrane. Even though on the bag you can't really see the holes, there are holes in there that allow certain size things to flow through. And you can see really our kind of solution guys can kind of come in and out, but our colloids and our suspensions get trapped. So I think that might be the experiment you're doing this week. You got the bag, let it go for so long, test the water or liquid outside the bag to see what came out. Eventually you'll pop that bag open and see what's still trapped inside. So you should be able to see the solution molecules flow in and out of the membrane. The colloids and the suspension should get trapped there. Then you could filter what's in there through a filter, and you'll see your suspension get trapped on the filter paper. Any questions on that there? Another sort of process of solutions is what's known as osmosis. And osmosis is the flow of solvent water molecules from a area of lower concentration to an area of higher concentration, usually through some type of membrane, semipermeable membrane. So if you had something like this, like a tube that's separated by a membrane here, and on one side you have salt water, and on the other side you have just pure water. And the process here by osmosis, what's going to happen is the water side of that membrane is less concentrated than the saltwater side. That's because water is a pure substance, has nothing dissolved in it. Salt water is water with a bunch of sodium chloride guys dissolved in it. So a lot of particles dissolved in there. So what's going to happen by osmosis is the water side here, the pure water side, is going to decide, I want to go to the right-hand side here, and I want to dilute down the more concentrated side. And it will flow water molecules across that membrane into the more concentrated solution. It will continue to flow until it hits a pressure that is sort of equal to the atmospheric pressure, and that's what's known as the osmotic pressure. So it'll hit the osmotic pressure, and it basically will stop the flow of water molecules from the left-hand side to the right-hand side, because now you got pressure kind of pushing back on it, so it can't evenly flow to the other side. Now, the osmotic pressure of a solution does depend on the number of particles or solute particles that are in that solution. The more solute particles you have in that solution, the greater the osmotic pressure will be. The pure water, as I mentioned, is a covalent molecule, which means you have no ions floating around, and that is going to be no osmotic pressure associated with that. By the way, the idea of reverse osmosis is if you apply a pressure greater than the atmospheric pressure back down the other way, that's going to shoot all your water molecules back across the membrane. If you have where that membrane is a lot of filters, you can filter out all the stuff you don't want and send basically pure water back the other way, which is basically what reverse osmosis is. They apply a greater pressure than the atmospheric pressure, and it basically, instead of the water molecules naturally flowing that way, it pushes all the water molecules basically back the other way, and you can filter out, like I said, all the stuff you don't want in there. Now, you could actually calculate a sort of concentration that's related to osmotic pressure and that is what is sometimes referred to as the osmolarity. And the osmolarity is equal to I times the molarity. So what is I? I is basically the number of particles, ions that are present. So for example, if we took a guy that has 2 molar sodium chloride versus 2 molar calcium chloride, and we wanted to know, for example, which one has the greater osmotic pressure. When we look at something like sodium chloride, it will break apart into a sodium ion and a chloride ion, right? So one of each. And in this case, if we were to calculate I, it is as simple as how many ions. So that is 2 ions. I would equal 2 in this case, which means if we calculate the osmolarity for my sodium chloride solution, the osmolarity or osmolality, molarity is sometimes referred to as osmol, is equal to I times the molarity. So I is 2, the molarity is 2 molar. This would have a 4 osmolarity, basically. Now, if we did this exact same calculation for the calcium chloride here would break apart in solution into 1 calcium ion, and we would actually get 2 chloride ions. So I, in this case, should equal 3, yeah? 2 chloride ions and 1 calcium is a grand total of 3 particles floating around in that solution for every one that you put in there. So if we calculate the osmolarity for the same 2 molar solution of calcium chloride, and we did it for calcium chloride, we would get 3 times 2 molar, which means 6 osmolarity. Which one has the higher osmolarity? It is the calcium chloride. It has a greater osmotic pressure because it has more particles floating around in the solution. So anything that has more particles or ions floating around in the solution will have a greater osmotic pressure, because frankly, what's really happening is those particles get in the way of everything. So it gets in the way of the natural process, for example, of solutions freezing, boiling, and all those things, because there's a lot more stuff floating around. So the solvent molecules that want to come together, for example, to freeze, now has to get around all these other things that are in there to come together. If they want to go boil themselves as well, they also got to kind of get around all those things to escape the liquid, because there's a lot more stuff floating around in there. That's, for example, what is known as a colligative property of a solution. It's dependent on how many particles are in there. You might have heard of boiling point elevation or freezing point depression. That is where you add something to a solution and it alters the normal boiling point of something like water. For example, that's why we put antifreeze in our car. Antifreeze actually does both things, because when you put antifreeze in your car where you have water, there's now a lot of particles in there. So instead of your water normally boiling at 100 degrees Celsius, now it will boil at a much higher degree Celsius, which is really good if you live in a hot climate, right? So your car doesn't overboil when you're driving around. Also, it does the opposite thing if you live in a really cold environment. Say your water freezing in your car at 0 degrees Celsius, it goes below 0. So if you live in a really cold environment, it prevents all your water in your car from actually freezing. And that's all a result of particles basically floating around in that water or in that solution. When you add the antifreeze to it, it's able to affect properties of solutions where things normally would boil, freeze, pressure, all those things are affected by it. As more particles you have, the more effect it will have on it. Any questions on that there? So let's also talk about 3 ways to classify solutions. That is isotonic, hypotonic, and hypertonic solutions. So isotonic solutions have the same osmotic pressure as body fluids. Most IVs are isotonic. So what's considered an isotonic solution? 0.9% mass to volume sodium chloride or saline solution. Could be any type, potassium chloride, whatever it may be. and 5% glucose is considered isotonic. Sugar solution and a salt solution, basically, or a saline solution. So those numbers are important to know because those are basically your numbers that either the solution is those numbers and they're isotonic, or they're too high or too low, and then you're in some trouble. Why is it important to have isotonic solutions, perhaps especially when you're given it as an IV? Well, I imagine if you're getting an IV, you're maybe in some issues, so you don't want to cause any more issues. So by doing so, the osmotic pressure inside, for example, your red blood cell and outside is the same, which means you're going to have pretty much equal flow of, say, solution, water, whatever you want to call it, fluid, in and out of the cell, which obviously is not going to cause any more damage to your cells, which you would not want that to happen, obviously, in that case. But if you give somebody perhaps a hypotonic solution, hypo means lower than, so that would be a solution that is lower than 0.9% sodium chloride, lower than 5% glucose. What's going to happen is you're going to run into some trouble. So if you take your red blood cell and you put it into a hypotonic solution, that means that outside of the cell is now less concentrated than inside the cell. And what's going to happen by osmosis is outside of the cell is going to go, I need to go into the cell to dilute it down. I got to send everybody into the cell, which, if you imagine like a balloon, is going to start to swell, basically, and could burst, which is known hemolysis, which probably not a great thing, I imagine, in that case. And again, that's because in this case, we have a difference in the osmotic pressure. The cell itself has more osmotic pressure than the water or what hypotonic solution that you got in there. So we're going to get that osmosis flow into it, going to swell and burst. Now, the opposite will happen if you put it into a hypertonic solution, and that means greater than, and again, it's these cutoffs. So you're either above 5% glucose or you're above 0.9% sodium chloride. And now if you put your red blood cell there into a hypertonic solution, outside of the cell is actually now more concentrated than inside the cell. So the same thing's going to happen. You have a difference in osmotic pressure between the cell and the solution. And through osmosis, the cell's going to go, oh, outside is way more concentrated. Let me help. And it's just going to send all of its fluid out of its cell. And what that's going to happen is this red blood cell, for example, is going to shrink and go through what's known as crenation, also not probably a great deal good thing happening in that case. So osmosis here is going to cause the flow of the solution either in or out of the cell in a hypotonic or hypertonic solution. But again, if you have an isotonic solution, because you got equal osmotic pressure basically on both sides of the cell actually here is acting as this semipermeable membrane, right? It's allowing things to flow in and out of it. You'll have equal flow of fluid in and out. Everything will be okay. Any questions on that there? So there's a table, what we just talked about there. So again, here, if we look, we have our isotonic. I like to call it the regular donut. Yeah. We have our hypotonic where it gets swollen, the jelly donut that's going to burst out. And then obviously we have our hypertonic where it's going to shrink like our donut hole, right? As we got going on in that case. So what will happen here if we put a red blood cell in the following? Let's do a 4% sodium chloride solution, a 2% glucose solution, a 0.9% sodium chloride solution. We put it in pure water. Will it shrink? Will it swell? Will it be okay? Will it go through hemolysis, crenation? Take a moment, decide what's going to happen in each of these cases. Let's take a look. So remember when you're doing these, those two cutoffs are really important to remember. 0.9% saline or sodium chloride and 5% glucose. Again, these are considered isotonic. So here it is as simple as 4% sodium chloride is higher, right, than 0.9%. So that's going to make it a hypertonic solution. So again, in this case, that means that our red blood cell, we're going to have a hypertonic solution. So outside is more concentrated than inside. So we're going to have everybody rushing out and it's going to shrink, right? And that is going to go through crenation in this case, right? Any question on that one there? Now, 2% glucose, 5% is our isotonic, so 2% is less than, which means we're going to get really the middle guy here. That's going to be a hypotonic solution. So when we put our red blood cell there into our hypotonic solution, everybody's going to rush inside because it's less concentrated on the outside. That's going to cause our cell to swell and burst, which is known as hemolysis in that case. Question on that one. 0.9% sodium chloride, that's dead on. So that is going to be an isotonic solution. And we're going to be okay on our cell there as it's going to flow in and out. No problem, the fluid. What about pure water? Pure water is hypotonic, right? One of those places where water is not the best thing, right? So pure water has no osmotic pressure because it has nothing dissolved in it, which means it is going to be hypotonic. And again, that's going to cause outside the cell to be less concentrated inside. So we're going to get this situation here where everybody's going to rush in, and that's going to cause it to swell and burst basically and go through hemolysis. Any questions on that there? All right. Lastly here, dialysis is a process similar to osmosis. It's kind of what you're going to do this week with the dialysis bag. Again, it pretty much has holes in it and allow, again, basically size restriction, certain size molecules to flow in and out of the cell. We also, in our bodies, right, use dialysis, right, to filter out things that we don't want, right? And sometimes people have trouble with that, so they need to go get dialysis to help them sort of filter out processes or stuff in their obviously body that needs to be sort of taken out if it's not working properly. In the laboratory, we oftentimes will do something very similar to what you're doing this week. I think in lab, you'll use a dialysis bag and put it in there. So, for example, in the lab, if you were doing some type of research on, say, a protein or something like that, that's in the body, say at a specific pH, you could put your protein in a dialysis bag, you could drop it into a solution that's at that pH and let it sit there for a while, and it'll come to equilibrium and be in the same sort of environment as it was, say, in your body. And then you can go do your kind of experiment on it, and you'll have a more real life sort of situation. So in lab and we sometimes will use dialysis to do those type of things, to sort of incubate things, also to allow certain things to exit the bag. For example, we want to again filter out something much like the body does that we may not want. Any questions on any of that there? All right, that is chapter 9. Okay, we're going to continue on, and we are now off to, dare I say, chapter 10. The very last chapter that you'll need a calculator for, right? Then you could just throw your calculator not too far because you'll need it for some exams, but you can put your calculator away for the rest of the semester after this one, but there is a lot of calculations in this one just to finish it up on here. So we're going to talk about acid and bases here, and let's get into it. So some characteristics of acids and also bases. So acids have a sour taste. So we see acids like acetic acid, which is the major acid there in vinegar, citric acid in fruit and stuff like that. They will change litmus paper from blue to red. So litmus paper is pieces of paper. A lot of times it comes in blue or red, and sometimes comes kind of neutral color as well, more of a purple. But typically, if you touch a solution to litmus paper and it turns red or stays red, it means that that solution is acidic. They also react with certain metals, like we talked about, single replacement reactions. Like if I take some zinc and some hydrochloric acid, it will do a single replacement reaction and kick out the hydrogen and make some zinc chloride and some hydrogen gas. And you typically will see the metal sort of go away at that point. I'll balance it like I'm in chemistry class here, I suppose. Put a 2 in there. They also are strong electrolytes. So strong acids are strong electrolytes, which means they conduct electricity. Weak acids as well are weak electrolytes, and they can also conduct electricity. Bases, on the other hand, have a bitter taste. They feel very slippery. A lot of soaps like drain cleaner, Drano, that type of stuff, are all bases. They also will change litmus paper to blue. So again, if you touch a piece of litmus paper with a solution and it turns blue or sort of stays blue, that also means that it is going to be a basic solution. There's also strong bases along with weak bases, which are both strong and weak electrolytes, which means that they will produce ions in solution and conduct electricity. When we talk about acids, just a quick nomenclature type of thing. When we name acids, it does involve whether or not there is oxygen is really the main thing that we look at when we go to name acids. And if the answer is no oxygen, the acid will start with hydro something ic acid. So like HCl is hydrochloric acid. HBr, which does not have obviously oxygen, is hydrobromic acid. The missing part is the negative ion that's attached. For all acids, the cation or the positive ion is H plus. So the positive guy for all acids is H plus. That's because that's pretty much the definition of an acid, as we'll talk about, is the ability to basically give away that H plus. Now, if it does have oxygen, it will contain one of those polyatomic ions. And if you remember, those polyatomic ions ends in one of two ways, either ate or ite for the most of them. And if your polyatomic ion for your acid ends in ate, your acid name will be something ic acid, like HNO3. NO3 is NO3 minus, which is nitrate. That means that my acid name here is nitric acid. H2SO4. SO4 is SO4 2 minus, which is sulfate. That's also why there's two hydrogens here to balance out the charge like a normal ionic compound. And this would be sulfuric acid. If you ate too much, you feel icky. That's a good way to remember that, I suppose. If your polyatomic ion ends in ITE, and your acid obviously has oxygen in that case, it is something OUS acid, like HNO2. And NO2 is NO2 minus, which is nitrite. This would then be nitrous acid. So this is a quick way to name acids so you know what the names go with, perhaps. That's the way you basically do it. We also typically will put the AQ symbol next to it, AQ symbol for aqueous next to acids, because they are in solutions. That's also why when we have something like HCl that's a gas, we call it hydrogen chloride. But when this gets dissolved in water, it becomes hydrochloric acid, and there's ions floating around basically in it. Any questions on that 2-second naming about acids? So that way when we see an acid, hopefully you'll figure out the name, I hope. All right. There is no hydro, though, in any acid that has oxygen. So if it has oxygen, it should not have hydro. The hydro part is always for no oxygens when you do it. Any questions on that there? All right. So let's talk about acids in general. So acids are substances that have the ability to produce H plus ions or hydrogen ions in solution. They are also sometimes referred to as protons when you're talking about acid-base chemistry, because hydrogen has 1 proton, 1 electron, no neutrons. So the only way you become positive is you lose your electron, and that leaves it just a proton. So it's sometimes referred to as a proton in this case. Also, in acid-base chemistry, anywhere you see H plus, you could change it out for H3O plus. This is what is known as the hydronium ion. They both basically in acid-base chemistry mean the exact same thing. They basically mean the acid part of that solution. So anywhere in equations, anywhere in formulas that you see H3O plus, you can exchange it out for H plus. I will personally probably use H plus most of the time. I will say books nowadays are rolling more towards using H3O plus and a lot of things. So again, anywhere I use H plus, you can put H3O plus, means the exact same thing. It's used interchangeable both in equations and formulas. Now there are strong acids, which are strong electrolytes. They will 100% break apart into ions in solution. So if you had something like nitric acid, which is a strong electrolyte, and a strong acid. When you have that solution, you pretty much only have ions floating around, like H plus ions, nitrate ions. And because this thing will 100% break apart into ions, it will produce a lot of H plus very quickly, which is why it's a strong acid, because pretty much the only thing it needs to do to produce H plus is go for a swim. As soon as it goes for a swim, H pluses appear everywhere. A lot of H pluses in that solution is going to make that solution acidic, and why it's a strong acid. A list of some strong acids, which I might have put up before, but there's pretty much 6 sort of strong acids: HCl, hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and actually perchloric acid. That list of kind of 6 strong acids is pretty much your 6 strong acids. The reason it's good to know those 6 is because if it's not one of those 6, it's probably a weak acid. So it's a good way to know if it's a weak acid or not. If it's not one of those 6, pretty safe bet it's going to be a weak acid. Any questions on that? So again, a strong acid is something that will completely break apart, able to generate a lot of free H plus. And that is the key. The H plus ions need to be free, or the H3O plus ions need to be freely floating, not attached to anything. That's what makes something an acid, is that ability to release that. That's why when we just talked about a second ago that the cation for all acids is H plus, that's why. That's the H plus that pops off and goes into solution and starts floating around, and what makes that basically an acid. Now, bases, on the other hand, have the ability to produce hydroxide ions, OH minus ions in solution. It's kind of the same idea as the acid, except for the base. It has that ability to produce in a solution a bunch of free OH minus ions floating around. Now, there are strong bases, which are also strong electrolytes. Most strong bases have hydroxide in the actual formula, like sodium hydroxide and potassium hydroxide. If you had a solution of sodium hydroxide, 100% of what you would have in that solution are the sodium ions and the hydroxide ions. You would have none of the NaOH still together. It's just going to completely fall apart basically in solution. And because of that, you will have a solution, for example, that has a bunch of sodium ions, which is not super important, but really in terms of the base, it is these guys that are floating around. The generation of a bunch of OH minuses in that solution freely floating around is going to make that pretty much a basic solution. As we will talk about shortly, the ratio of how much H plus and OH minus you have in that solution will tell you what it will be. Will it be acidic, basic, or even if it's neutral, they happen to be equal amounts of both of those things in that solution. Pretty much if you go to the periodic table and you go where lithium is, you hang down there to sodium, you go to potassium, hang a right to calcium, strontium, barium. If you pretty much go group 1 or 2 on the periodic table and hook any of these guys up with hydroxide, those are probably going to be strong bases. Yeah. Group 1 and 2. The reason group 1 and 2, group 1 is called what? It is called the alkali metals, right? That's group 1. Group 2 is called the alkaline earth metals. It's group 2. The word alkaline means basic. So that's where a lot of our strong bases come from. Pretty much OH minus hooked up with somebody in group 1 or group 2 on the periodic table. And that will usually be a pretty strong base. Not all bases, as we will see, is strong bases. There are weak bases. Probably the most common weak base, as we will see, that you will come across most likely is ammonia, is the most common weak base. So what happens with ammonia? Ammonia does not have OH in it. But what ammonia is able to do is ammonia is able to react with water and actually take an H plus from water. And it's able to make NH4 plus. And because it takes that H plus from water, it's able to produce hydroxide. So ammonia, even though it's not carrying the hydroxide with it, if you will, it's got to go do a little reaction. Because it's able to react and actually produce hydroxide, is still considered a base. That's also why ammonia is a weaker base than sodium hydroxide, because if you want to think about it, sodium hydroxide, frankly, has the hydroxide with it. So all it has to do is just go for a swim. It's going to release it. Ammonia's got to go find some water, do a little reaction to produce that hydroxide. They both have the ability to produce the OH minus, so they're both considered bases. But again, sodium hydroxide, and anybody really from group 1 or group 2 that has hydroxide in it will be able to just release that hydroxide and make it a much stronger base than something like ammonia, which is, again, probably the most common weak base that you would come across. Any questions on that there? So what happens when we react a strong acid with a strong base? Pretty much the fundamental reaction that you have is the formation of water. And if you remember, that is one of the 3 reasons why a reaction takes place, is that you basically made water. So whenever you take basically a strong acid plus a strong base, you will make 2 things. You will make a salt and you will make water. A salt is just an ionic compound. So what's happening if you took hydrochloric acid and you reacted it with sodium hydroxide, which is a strong acid, strong base. It is also, as you might recognize, one of those that fall under the umbrella of double displacement reaction that we talked about, right? So this is still a double displacement reaction because this is a strong electrolyte. You have H plus and Cl minus, basically the 2 ions that are there. And you have sodium ion and hydroxide ion from our base. Remember, in a double displacement reaction, we're going to swap partners basically, right? And when you get H plus and OH minus, those guys come together to make the water. So that is always how the water is made, from the H plus from the acid, the OH minus from the base. In this situation is always where the water comes from. The other 2 things come together and makes an ionic compound like sodium chloride. That is what is referred to as the salt in this case, which is just an ionic compound. So if you remember, these are under the umbrella of double displacement reactions. These are the guys that basically make water as what's really happening. If you take any combination of strong acid and strong base and you put them together, whichever one you like, nitric acid and potassium hydroxide, whatever you like, and you boil it down, this is ultimately the reaction that's happening. The H plus from the acid, the OH minus from the base come together, and you're basically making water, which is why these are referred to sometimes again as acid-base neutralization reactions, because you're making water is basically ultimately what you are doing in that. And that's also the reason why this reaction is taking place. Any questions on that there? Yeah. All right. So that's what we see here. That's okay. We don't have to look at that one. I think that's what we just talked about. Here are a couple of other examples. Here we have nitric acid and potassium hydroxide. Once again, same idea here. Nitric acid, which is a strong acid, plus potassium hydroxide, which is a strong base. Once again, double displacement reaction, positive, negative, two ionic compounds basically together. This guy, basic units, H plus, which is always for the acid, and nitrate. This guy, potassium ion and hydroxide. Once again, we're going to switch partners, and we will get our water from the combination of the acid and base. And now we could get our salt, K plus, NO3 minus. One of each of those, just like we did with nomenclature, will give us our salt and water. This reaction. Any questions on that? Again, if you take this reaction down to the basic bare bones of what's happening, it is basically the H plus again coming together with the OH minus to make water. That essentially is ultimately what is happening in this reaction. Any questions on that there? All right, why don't you try one here? Maybe. What do you get if you take HCl and react it with, say, calcium hydroxide? And what do you get if you take sulfuric acid and react it with potassium hydroxide? All right, so finish up what you get there. Again, some strong acids and strong base. Okay, let's take a look and see. So again, as soon as you recognize this as an acid and a base, you should know that you will get salt and water, basically. So you can almost pre-fill in the water if you want. Yeah. So again, double displacement sort of deal happening here. So we want to think about the basic units that make this up. So that's H plus and Cl minus. This is calcium, which is group 2, has a +2 charge. That is hydroxide, which is a polyatomic ion. Again, we know we're going to switch partners, right? So that is where our water is going to come from right there. That H plus and OH minus is basically come together to make our water. We then also want to put our salt together, just like we did with nomenclature. We need to equal it out to 0, right? So we got a +2 for the calcium, a -1 for the chloride. That means we do need one more of those chlorides to balance it out. And that will give us our proper formula here for our salt. Any questions on how we got to those formulas? Yeah.
Hydrogen, I know what's the H plus, and then on the other side is OH, but there's 2 of them.
Right. I'm not worrying about the balancing part right now. I just want to make sure I get the proper formulas. So what you want to always do is, if you need to kind of put these guys together in like a double displacement situation like this, what you really want to think about is not the balancing that there's like 2 of those guys on this side or 1 of those guys on this side, is you want to think about the guys on the left-hand side and what are just the basic 2 ions that make that up, basically, regardless if there's more than 1 of each. you know, so basically that HCl is just H plus and Cl minus, and the basic two ions that make up the second guy, the calcium hydroxide, is a calcium ion and a hydroxide ion. That will allow you to properly put together the formulas on the other side. And then what you want to do is once you have the formulas, we do need to make sure it's balanced, which in this case, it is not balanced. So we do need to go back and put some coefficients in front if that's your question. And in this case, what we would need to do is probably put a 2 here. That will give us 2 chlorides on each side. That would also give us now 2 hydrogens there and 2 hydrogens there, which means over here in front of my water, which I probably shouldn't put a circle around it, we would also need a 2 there. And at that point, we should now be balanced in terms of the equation. And that's where you'll take care of the extra, you know, there's like 2 of those hydroxides and stuff like that. Is you always, if you have a situation like this, want to make sure you just get down the proper formulas first and then go back and do the balancing with the coefficients. So often people try to do that together, they write the wrong formula. And you end up with something that will never balance because you're not starting with the right formulas. So you always want to kind of start with the right formulas and then go back and coefficient to balance it out. Yeah. What's that?
So when you go to balance, you're balancing the formula that you just created.
Yeah, exactly. So you want to balance the correct formulas in the equation, right? So you don't want to start with the wrong ones. So for example, something like this, you know, sometimes somebody might put, you know, or maybe a better example, like, you know, if you had on, say, this side, like Na2S plus like, we'll do something like this, say like this. All right. So sometimes this is also going to be, for example, a double displacement reaction. And sometimes when people go, okay, these two guys are going to come together, they go, oh, there's 2's on both sides. So this is the formula I want to write and keep the 2's. And that's incorrect. So you shouldn't do it that way. You should always just go, okay, the basic unit of sodium is that, the basic unit of sulfide is that, the basic unit of calcium is this, and the basic unit of nitrate is that. Now when you put it together, you'll get the proper formula, and then at the end you could go back probably and put a 2 in front of it to balance, you know, whatever you need. So you always want to get that formula correct first, just like you're doing like nomenclature and you're putting those ions together. And that's why you want to look at it as not how many of each of those ions they have on the left-hand side to begin with, but what is just one of those ions, what's the charge? That way you can put them together to get the proper formula. It's a very common mistake when people have to kind of predict what's on the other side is they try to do both of those things together. Like it makes sense because you see the two. So they try to balance and write the formula at the same time. The thing you want to remember is you always should go with formula first, correct, then balance. Yeah. And that's always the order that you want to do it. Other questions on that? So if we come down and look at the bottom one there, we have again an acid, again a base. So we're going to do the same thing. It also is a double displacement here. So we're going to, even though there might be extra numbers there, we're just going to think about what are the basic ions here. So we know for every acid, the positive guy is H plus. Again, I'm not concerned at this point that there's a 2 next to it there on the left. That's the most important thing here is to get the formula. We also want to make sure we get the proper formula there for sulfate, which is SO4 2 minus. Now for potassium, same deal, K plus and OH minus. Now again, when I put this together, I could clearly see the water and not something funky like H2 hydroxide or hydrogen peroxide or something like that. So that is again where the water is going to come from, the combination there. That's also going to help me when I come to this guy. Again, like nomenclature, I got a +1 and a -2. Now I know to get the proper formula, I need 2 of those positive guys, and that will give me my K2SO4, which again is my water and salt. Now that I did that, I could check off I got the right formulas. Going to make the balancing a lot easier because you have the right formulas there. Now we could go back and do coefficients and balance it. So probably a 2 there and a 2 there, I think, and then we should be good at that point. So that again is the order you want to do it. Always when you're doing any type of double displacement, putting ions together, basic, just one of each of those ions, what they are, put it together, proper formula, then balance. That's always the order you want to make sure you do it in. Then you will hopefully never go wrong. But it is a very common mistake. People always try to combo those steps. Any questions on any of that? So the take-home message here for us: salt, acid, base. You get a salt and water. Water always, again, H plus from the acid, OH minus from the base. And the salt is basically the two ions that are left over from that. Put them together properly, and that will get you your salt. Any questions on that there? Okay. So now that I wrote all over this page, let's get into some proper definitions here. Let me erase all that. There you go. All right. So the first sort of early definition of an acid and a base was a guy by the name of Arrhenius. He did experiments with electrolytes. And again, he defined an acid as anything that has the ability to produce that H plus ion in solution, while he defined a base as something that's able to produce OH minus in solution, as we've been talking about. Again, that is really your definition of an acid and base is it able to release that H plus into the solution, or is it able to release that OH minus into the solution, which will make it either the acid or the base. And some examples here: if you take hydrogen gas and you bubble it through water, you basically get hydrochloric acid. And that again is why we have it in the aqueous sort of version there. We use aqueous for acids because that is where we find ions. Ions are in solution floating around, and that is basically what we need to happen for it to be an acid. In the gas version, they're actually sharing electrons and they're together, they're moving around as a unit. But when they sort of get into there with the water, they get hydrated and release that. Same thing here with our sodium hydroxide. They're going to be able to produce that hydroxide. Now, the Arrhenius concept was a really good sort of first step in terms of acid and bases, but it was limited because most of his work was done with bases that actually contain hydroxide in it. And as I mentioned earlier, there are bases that don't have hydroxide in it, but are still bases because they're able to produce hydroxide. So a more general definition of acid and bases is one that was put forth by what's known as Bronsted and Lowry. And that is the Bronsted Lowry definition of an acid and a base. And they said that an acid is a proton donor. And that again is an H plus. And the importance of this is the positive charge there. That positive charge, when somebody loses an H plus or somebody gains an H plus, will affect the overall charge of what happens, right? So for example, if I lose a proton or an H plus, do I become more negative or more positive? You do become more negative. You think about it, right? You have less protons, more electrons, right? So you become more negative. And if somebody gains the H plus, they become more positive, right? Because they now have more protons than electrons. So that part of the relationship for Bronsted Lowry is oftentimes sort of missed by people. They just think about the H part, but that plus part is really important because it will affect charges on things that are either gaining it or losing the H plus. And again, a base is something that will accept an H plus or a proton. And again, when it does accept that proton, it's going to become one more positive as it gains that H plus. So the general definition here of Bronsted Lowry is we have an acid and we have a base. And this is a generic sort of formula for an acid. And in this case, the water here is going to actually act as the base. And what's going to happen is the acid's going to donate the H plus over to the water. The result of that, as I mentioned a second ago, is my HA now has one less hydrogen and also becomes negative because it was neutral to begin with. So when it loses the positive charge, it becomes one more negative on the other side. The water, which is neutral, will gain a hydrogen and become H3 and also become a positive charge because it's gaining the H plus. It creates partners in the Bronsted Lowry definition. This acid is related to this guy on the right-hand side. This is what is known as the conjugate base. This base is related to the guy on the right-hand side. This is what is known as the conjugate acid. So the definition of Bronsted Lowry actually will create partners on opposite sides of the arrow that are related to each other by 1H plus only. There's only a 1H plus difference between those. And that can be the only difference for these guys to be partnered. Now, for example, if you take HCl and you want to describe HCl dissolving in water, basically, you could do that reaction. Here, the HCl is going to be my acid. The water is going to be my base. The HCl is going to donate over here the H plus, which is what the acid will do. When I do that, that is going to create H3O plus over here when the water gains it. And my HCl will lose an H plus and become Cl minus. So this is the acid. Over here is the conjugate base. This is the base. H3O plus is the conjugate acid. The only difference is as you go from your acid to your conjugate base, it has one less H plus. That H plus came over here. And as you go from your base to your conjugate acid, it has one more H plus. And that again is why the only difference between these things can only be one H plus. If it is more than one H plus, then they are not partners or pairs. It can only be that one H plus difference. Nothing else can change. This is also why, for example, the equation that I just wrote is basically just describing hydrochloric acid dissolving basically in water, basically. You could also write that equation more simplified, which is HCl goes to H plus and Cl minus. And that is why we talked about earlier, H plus, H3O plus are essentially the same thing. We typically will get H3O plus when we include water in the equation, when we write an acid sort of breaking apart in solution. If you don't include the H2O, you won't get the H3O plus. So that's why H3O plus and H plus are basically interchangeable. They represent basically the same thing. They represent that acid releasing basically the H plus or the H3O plus into that solution and being an acid. In this case, you wouldn't see both the acid and base here. You just see sort of your acid and your conjugate base and your conjugate acid on the other side. Any questions on that there? All right, so as I mentioned before, there's our HCl example. And again, it can only be that difference of one H plus. Also, like I showed you with ammonia, for example, that we looked at earlier, that equation. In this equation, the ammonia is acting as the base. The water is acting as the acid. So once again, in this case, the water is going to actually send the H plus over. That will create our NH4 plus and our OH minus in this case. This would be the base, and over here would be our conjugate acid. This would be the acid, and over here would be our conjugate base. Again, the only difference is one H plus difference that in this case is actually being sent over to the ammonia from the water. By the way, in the reaction here, water is what? On the bottom, water is the acid or the base? It is the base, right? In this reaction, water is the acid. Water actually can act both ways. It can act as an acid or a base. There are certain things that can do both things, and those are things that are known as being amphoteric. An amphoteric is something that could act as an acid or a base. And water is a sort of prime example of that. It has the ability basically to do both things. It could act as an acid in certain situations, or it can actually act as a base in certain situations. questions on that there? Yeah. In the NH3, in this case up here, we used the writing part, that helps. In this one, it is acting as the acid because it is the one that's going to supply the H plus over to the NH3. In the bottom one here, it's actually going to be the one that's going to receive from the HCl. It's going to receive the H plus in that case. And water does have the ability basically to do that. There's other substances we will see that has the ability basically to do both things. But water is one of those ones that actually can do both things. It can act either as an acid or a base. Yeah. I would say in your case here, it would be what is going to react with. So you probably would be able to recognize either whatever it's reacting with as either an acid or a base. And then it would be pretty much the opposite. It would do the opposite thing. So if you see something like HCl, like we see in the bottom, or HBr or HNO3, anything that you could identify as, oh, that's an acid, for sure, that's going to be the one who's going to donate. And then water will be the one receiving. If you have water and you see something that it doesn't look like an acid, but it's probably a base, then that's definitely going to be the one where it's going to donate. So it's really probably for our purposes here, whatever is going to react with water in the sense would be how you would determine. That's really the one you would want to look at and try to identify what that thing is. Is it an acid or base? And then water would do the opposite of it. Yeah. Other questions? Now, I would say in both of these cases, just so we're understanding, both of these reactions, they are technically a reaction happening, but basically both of these are basically just showing you these guys basically dissolving in water is basically what this sort of reaction is happening. And that's what we see here again, because in this case, we are reacting with the HCl, which definitely is an acid. We know in this case, the water is going to receive that H plus and act at the base. And again, when you do have water in the equation, that's where we produce our H3O plus or our hydronium ion, which is basically the acid part of the solution. This is also why this is considered an acid, because when it dissolves in water, again, we are producing H3O plus or H plus, whichever way you want to look at it. And again, it's that production of that H plus or H3O plus, which makes it, again, an acid in this particular case. All right, so why don't you take a second here. What we're looking for is which combinations here would represent a conjugate acid-base pair. So take a few moments there, decide if any of these would be considered pairs. Okay, so let's take a look. So hopefully you know at this point that really this is the only difference that we could have. So for these guys to be partners, the only difference between the two has to be 1H plus. Again, if it's more than 1H plus, then they are not partners. So there's a couple ways you can look at it, however you want to do. If we take up the first combination here, if you take the H off of this, and the plus, you are left with this, and because of the plus, it becomes one more minus, they match. So this would be a pair, as the only difference is. Alternatively, you can put the H plus onto this guy and you end up with this guy, so they work out whichever way you want to do it. Here, if we look at HCl and ClO minus, the difference between this is an H plus, but there's also a difference of an oxygen, right? So that means that these guys are not pairs. It can only be an H plus difference, nothing more. If we look at H2PO4 minus and HPO42 minus, again, however you want to do it, if you want to take the H off, I'm going to remove an H, which leaves me HPO4, and I also remove the plus, which means I become one more negative, right? And now they match, so they are going to be pairs. Or you can put the H plus onto this guy, and you'll end up basically with this guy here, if you want to go that way and look at it that way. Lastly, here we have HNO3 and NO3 minus. Same idea, I'm going to take off an H. And also when I take off an H, it also is the plus, which makes it one more negative. and they match. So, or again, you can put the H plus onto this guy and you'll end up with that guy right there. So however you want to look at it, take the H plus off or put it on. But again, when you do take it off or add it, you do have to adjust the charge. So that positive part's really important as well. Any questions on that there? All right, we will lay it up there for today.